Imagine a world where adversaries could access any source code, even programs written by banks or many other enterprises. They could test their program locally. They can have a simulated environment locally with that targeted program. They can run that program with the real data to find for security bugs. They can build their exploit. They can test their exploit and find if there is any flaw in that exploit. When it comes to running the attack, the adversary can remain anonymous. Sounds like a scary word, right? Welcome to the Smart Contract Security. I will dive into a bit of fundamentals for a smart contract from a security angle. Even if you are not familiar with the smart contract, this introduction will give you an overview about the things that matter to us when it comes to the security assessment of smart contracts. Smart contracts, think about them, is like a program that runs. But this program runs in a specific machine, which here we refer them as a Ethereum virtual machine or EVM. What is Ethereum? Think about Ethereum is the Bitcoin network. So we have a network of accounts and transactions plus a state machine. Or a state machine in another sense that it's a network that you can run code. EVM or Ethereum virtual machine is a machine that executes those smart contracts in a decentralized way. Think about a program that runs in a distributed network. And blockchain is that distributed network of those EVM machines. And one of the uniqueness of the blockchain is a network that can be trusted due to the way that it is designed. And finally, Solidity. This is another term that you may hear. It's a programming language to develop smart contracts, similar to many other languages that we have. In this network, we need a language to build these code, which we will get to the detail of that a little bit later. Let me give you an analogy between a smart contract and web app. Perhaps that can clarify how things are quite different when it comes to EVM. First thing is, both web apps and smart contracts, by the end of the day, the code need to be compiled to the bytecode. So if you are familiar with assembly or a machine code, x32 or x64 bytecodes, it's similar. Obviously, in a smart contract world, we have a limited set of bytecode, which toward the end of today's presentation, we're gonna see some of those codes. The other interesting thing that we should remember, there is a lot of relearning needs to happen when we approach smart contracts, and that's to do with one of them to do with the way that the clients or users are able to send a request. So in a typical web app, a client or a browser will make a HTTP request over a TLS to a server, and it will receive response. And this communication typically is one-on-one. So, and then by the time it will send a request, that will be processed by the server. That is not the case in a smart contract world, where the messages are public. Effectively, if I want to send a request to buy something or sell something, first, I will create a request, and the request in a smart contract world is referred as a message call, or in other sense, transactions. And this transaction or message call will be sent to a pool, like a public pool of messages. And I will talk about how this will be processed later. So we are not talking about the model of a client and server here. We're talking about a shared model that messages are public. Now, from a security standpoint, now immediately you can think about a number of issues or attack profile related to this way of invocation. When it comes to responses, In a web app world, well, we send the HTTP request, we receive the response back almost immediately. Again, that is not the case when it comes to smart contracts. We create the request, then this request will be broadcasted to the network, that blockchain that we talked about, and then we need to wait for one of those EVM machines, or better to say nodes, or better than that, miners. They pick the message. So effectively, those miners are like servers that are going to process that message, that request that we want to do. And then that can take a few seconds, up to, could be in some cases quite longer than that. So it's not immediate. And then this doesn't guarantee that everything is final. Now, by final, what I mean is, when it comes to the HTTP, once you get the response back from a server, that's it. That response is final. When it comes to the smart contract world, there's a notion that your response is 99% final, saying that you want to purchase something. After a couple of seconds, once the miner, so you will create the request, you broadcast it. After a couple of seconds, let's say the miner will pick it up, will process it, and you will see the response of your purchase. You still need to wait for perhaps in some networks for a couple of minutes for this request to get finalized. There is another, well, security thing or happening in that network. Needs to make sure that all those miners, they behave in a trusted way. So all the other miners, they will verify the work. And that will take a time for other miners to verify it. It can happen that the request that we may send may get reverted back due to whatever reason. And finally, the things that could be, again, different here is related to the code. Now, in programming languages, we have the concept of mutability and immutability. So mutability is about you can change something, you can modify something, is effectively write many, read many. However, immutability is a concept where you will write once, but you can read many times. And that is to do with smart contracts. Once you written a code, compiled it, and put it in a blockchain, that's it. That is final. There is no way for us to go there and modify the code. Even if there is any bug in the code, unfortunately, there is no way to go and change it. Now, you may think here now, oh, this could create a network full of buggy programs. There are some software design patterns that can be followed to overcome, well, this restriction. However, this is the environment that we are dealing with. So hopefully by now you got some idea about different attack profile and environments that we have within the smart contract world. Let me also quickly compare the Ethereum virtual machine with a typical x64 machine, the laptops that we use and desktop that we use. First thing is, if you have done some computer science related courses before, or you remember, we have a concept of registers. For example, in x64, the CPU contains at least 16 registers, which CPU will use that for the majority of the arithmetic operations. In EVM, we don't have any registers. So we will see what's going to happen to that. But you most likely remember about the concept of a stack. Most likely you have heard about buffer overflow, stack overflows. Yes, we do have stacks in EVM, but we're not going to have the same buffer overflow that you have seen previously in a C or C++ languages here. When it comes to, in general, storage, now, typically, when we run a program and that program may produce some data, or it may have some database, things like that, all of that information potentially could be in a single environment. If it is on my own machine, it could be a single machine, but if it's a cloud server, multiple cloud machines, or backup of those cloud machines, we are talking about a limited subset of machines that will store the data. When it comes to the EVM, all the transactions, all the contracts are persistent on all the full nodes that are in the network. So effectively, you have a track record of all the things that happen throughout the time within the network or in that specific contract. This point actually makes it quite interesting, because if, for example, there is an attack or a compromise happen on a specific contract, and we can go and review it. We can go and have a look and see what sort of transaction caused that attack. You can also see, as I said, you can also access the bytecode and eventually the code for that contract and review it to find out what led to that compromise, because we have this audit track, let's say audit track of everything, or this information is persistent. Often I use a different terminology that might not be quite similar in a smart contract world, just to gives us this analogy so we can understand it better. When it comes to the execution, well, obviously the execution in an x64-bit, everything happens on a CPU, on a single machine. When it comes to the EVM, the nodes that are known as miners are in charge of executing those invocations, those requests that was received. The other thing is good for us to know is the size of effectively the word size. So the size of obviously the register on 64-bit machine is 64-bit. When it comes to the EVM, yes, we don't have registers, but the size of every item that we put on the stack is 256 bits. Why that it matters? We will see that later. So effectively, that is the fixed size that we're gonna deal with. And finally, just for completeness, our 64-bit machines are little endians, but EVM is big endian, like a network protocol. All right. When it comes for looking for vulns, where are the places that we can look for vulns in this smart contract world? Well, the technology stack is slightly different, but it's similar to the other network, other environments that we have dealt with. Obviously, the smart contract themselves can have vulnerabilities, which today we will go through one of them. The compiler that will compile that code to the bytecode, EVM bytecode, could have vulnerability, for example, Solidity. The implementation of the EVM may have some issues, like that nodes, that machine, the implementation of the protocol. And obviously, all the other protocols, the hashing algorithm, there are so many other protocols that I didn't cover here. The protocol itself may have the issue. For example, we may have an issue in a non-smart contract world. We may have issue with OpenSSL library, or we may have issue with TLS protocol. So if we have an issue with the TLS protocol, that perhaps similar to the item number 4 on the screen, or when we have issue with or OpenSSL library, this could be similar to item number 3, 2. One of the hashing algorithm, popular hashing algorithm used in a smart contract world is known as keycheck. It's similar to the SHA-3. And finally, the blockchain itself. And these days we have 2 layers of blockchain. Again, Ethereum is one of them that we are dealing with. There's also layer 2. But again, I'm not going to cover them here. The focus of this talk will be effectively on item number 1, which is a smart contract, which obviously has attracted quite many what is known to be blockchain engineers, which they attempt to write a code. And this code, like many other code, can have security bugs. And these security bugs we will see toward the conclusion of this talk that are quite different from what we are used to in a non-smart contract world. Okay, let me start with an incident that how an attack could look like in a smart contract environment. It was around April 2018 where someone stole that value that you see on the screen. So think about 8 with 61 zeros in front of it. So of a coin known as beauty coin in the smart contract world. Obviously, there has been some value for this coin in the network, but this number here is quite huge. So even you can think 1 with 60 zeros in front of it in a two transactions by exploiting an overflow vulnerability. So how the attack worked was related to a function within that contract of that beauty coin, a function within the beauty coin contract known as batch transfer. This function received an untrusted input, in this case value, and it performed arithmetic on this untrusted value, and that arithmetic resulted into an overflow, and the number will wrap around, which we will go through detail of that a bit later. The function itself, which was vulnerable, it looks as following. When it comes to the smart contracts, again, you typically find relatively the codes are a lot smaller than normal enterprise code that you may have the chance to review. And it's quite condensed. Now, the part that this function effectively, which had the vulnerability known as batch transfer, it will receive this value from an untrusted input, and it will perform an arithmetic right here using that value. And this will cause that issue. Now, there has been some talks and conversations around like typically how this overflow situation happened, but I think I want to use this opportunity to take one step back, because this specific one is nothing new. In fact, it's a historic bug that also finds its way into the smart contract world. And I want to go through a good solid foundation around why this bug is actually happening and why still today we're having this bug. So hopefully we can understand it. And when it comes to mitigating against this bug, we know what to do. It's not just following, hey, just download this library or go and get this version of a compiler and you're safe. I think it's given the fact that this bug is so old, I think we can do something better about it. So to give you this background, I want to move slightly to the non-smart contract world, because that will make a lot more sense for me to explain this bug. And then later on, we will see the implementation or the situation of this bug in a smart contract world. I mentioned about registers, and registers are effectively used for majority of the arithmetic operation in the CPU. Think about registers as like a tiny memories that are close to the CPU core, and CPU uses that for doing quick arithmetic operations. So rather than making a round trip call to a memory to, for example, receive the first value and then making another round trip call to memory to get the second value and then later on add them together, is a lot more performant to do it in the registers. As I mentioned it before, these registers can be 64-bit in a 64 machine or 32-bit in a 32 machine. And that means that the maximum number that we can store, or the maximum number of value that we can store on those registers, are limited. In a 32-bit system is 2 power 32 minus 1, and in a 64 system is 2 power 64 minus 1, or effectively these numbers that you can see here. So with that in mind, perhaps let's just focus on a 32-bit for a while and look at this number that you see here. Let me move into this code sample. So we have 3 local variables or variables that are declared as int. It's a 32-bit system. and it will receive a surcharge, it will receive a fee, and it tries to do this arithmetic, adding these two numbers together, and eventually pass around that value to a function to perform a transaction. So effectively, this number plus this number, well, we assume that that will still remain as a positive number. Well, out of the surprise, we may find out that that number suddenly will wrap around and will give us this negative number. And if you have seen in some payment system, a negative value often may result into a refund. So rather than we charge someone, we may end up giving them some huge refund back. Overflow, or integer overflow in this case. Why that happen? Two causes. One is integer type is stored, or integer value is stored as a fixed point format, meaning that we have a limited size that we allocate to store an integer number. In a 32-bit system, that is, well, 32 bits available. Now, one other thing that I didn't mention before is if we want to represent both positive and a negative number, or the other say if we want to represent a signed value, we need to reserve one of those bits to represent minus or plus. And that will divide that range that you have seen before into two. So although this number that we have seen here is a lot smaller than the range of 32-bit system, since we are dealing with a signed number to represent minus and pluses, we have effectively half of that range available to us. So that is the reason number one. One thing I want you to pay attention also here is that the least significant digit in a minus range is 8. The least significant digit in the plus range is 7. This is something that I have seen often we may overlook when we may do some range check in our code. Reason number two, that why this wraps around happen, this is to do with microprocessors, CPU including, implement what is known as a modulus arithmetics. And modulus arithmetic is used when value goes beyond that range that that register can store. Now, why there is such a design decision on a CPU, again, is not in the scope of this talk, but that is something by design that we are limited to. What is modulus arithmetic? Well, surprise, we actually do using it in our daily basis. Suppose if I go to a doctor and she prescribe me to take a medicine every 4 hours, if let's say if the time is 9 p.m. now, I know quickly that the next time that I need to take this medicine is 1 a.m. Well, what actually I did in my brain, I did modulus arithmetic, because 9 p.m. or 21 plus 4 equals to 25. Well, 25 is bigger than 24 because we don't have anything more than 24 in the time system. That is the overflow. 25 divided by 24, the remainder is 1, and that gives us our 1 a.m., and that is our modulus arithmetic. Now, you may agree with me in the context of the time, well, it makes perfect sense to use this arithmetic. But perhaps in the context of a typical, well, when you use calculator or things like that, it may not make that much sense. Now, going back to the example, that surcharge or that fee plus that surcharge will give us this value, and this value is bigger than, well, the range of a 32-bit system. So the modulus arithmetic kicks in, and it will end up getting this value. And this value, again, this is a way for us to represent a minus this number. So this is when that sign bit is set, and this will equivalent to this massive negative number. I didn't talk about 2's complement. Again, it's something basic, but that is how we represent negative numbers. Cool. So the root causes we're going to take from here is that When an untrusted data is assigned to a fixed size data type, in this case integer, with no range check, we're gonna have this issue. And the other thing is the value will wrap around due to modulus arithmetic. And the reason I'm emphasizing on number 2 is this is not the case, for example, with GPUs. GPU cards do not follow modulus arithmetic. Well, I leave that as a question that you can take. So due to these two facts, we are having what is known as a integer overflow. So in the context of the smart contracts, because we mostly deal with integer types, it's known as integer overflow. In other languages, I refer to this as numeric overflow because it's not only limited to the int type. So what are the common patterns or insecure patterns can cause integer overflow? So firstly, any arithmetic that we do using pluses, minuses, multiplies, divisions, and all the similar equivalents of those, exponentials, things like that. Now, perhaps the less known situation that could cause overflow are when we do bitwise operations, such as left shift. We will see an example of that a bit later. And most importantly, when we do casting, when, for example, when we cast from an int, perhaps 64-bit, 256-bit, back to 32, that is where also an overflow happens. Now, in a traditional, well, in the more like non-smart contract languages, such as, for example, Java or in Go, if we cast from a double or a long type back to integer, we also have the similar situation. Now, the scary part here is, not so scary part, but the problem here is that we're going to see these two issues still up until today has remained a problem in the smart contract world. All right, now you may have this question in your mind that, hey, you just told us that EVM doesn't even have a register, so why does this number still wraps around? Really good question. Once we move to the lab, I will actually show you that how effectively we have the same implementation of the same behavior, but using a stack in the EVM environment. Okay, so let's dig into our first lab. Now for the lab, I'm gonna head to learn.secteam.com. So I will just type it in for the people in the chat so you guys can follow along. And head to Solidity. Obviously, you need to first log in here and then move into Spec Overflow. This is effectively the issue that was related to the beauty chain or beauty coin contract that we discussed before. And then head to Numeric Overflow and hit on the download button here. This will give you a Git URL to clone locally. Right. Now let's move to my terminal, which I have already cloned this lab. Let's just start running this lab. So the way that this lab is set up, it will bring up a local blockchain in our machine using Docker, and it will compile that, the contract code which is in this lab, and then it will deploy it, and then we can interact with it as if that we are dealing with a real blockchain network. So to do that, similar to the conventions that we have in our other labs, you hit make build. This will go and build the contract code for us. If you see this sign, the program is ready to run, that means it's already compiled and your Docker image is available. So for this lab, as I mentioned before, you need a Docker compose, which you can download from, and make. Make is a command that is available by default on OS X, and also you have it on Linux. You can just simply download that. Cool. So once that happened, the next thing we want to write here is, well, let's just run this. It may take a while. The first thing it does, it will bring up blockchain. Well, that network, so it uses a program called Ganache to bring that up. And now it heads to running Solidity. And then don't worry too much about all these numbers and hash that you will see on the screen. As you work more with Solidity, it makes more sense. And now what we have here is a console, like a Python console or a shell that you can now interact with a contract that is already deployed on a blockchain. So as I said, there is no concept of servers and like clients here. If you want to send requests to smart contracts, first you need to write it, and compile it, then deploy it on a blockchain, and then start sending requests to it. So effectively now the part that is getting compiled and deployed is already done. Now the environment is available for us to start writing some, well, to interact with that smart contract. Now before I start doing it, I will show you the, let me go to, I will go through the structure of this a little bit. So inside the source directory, we have a folder called contracts. That is where the code sits in. And the other thing is test, which I will cover it a bit later. I'm using Truffle framework. Again, you don't need to worry about all these terms. This is just a framework I've used to build and deploy this contract in this lab. In the future lab, I actually use a different framework. So if we head and start opening up one of these contracts, which is Hello World, this is effectively the code that it has now already deployed in my local blockchain. From the top, well, we have a contract called Hello World. This contract has a function called store, which will receive an input 256, and it will store it in that local variable number here. And then we have a function called retrieve, which will return that value back to us. Okay, so with that, let's go back to our console. So what we're gonna do here is, first, let's get an instance of these contracts so we can interact with it. It's similar to how you create an instance of a class. You get an object, and then you can access all the methods and the properties of that object. This is same here. So let's, for example, say a variable called hello world HW equals to let's put it this way, hello world. You need to put await. This is a JavaScript framework, so we need to take care of all the async functions and deploy it. All right. So now I have an instance of this contract available to me, and I can see this instance does give me access to the store and the retrieve function. Let's go ahead and store some int value in the store function. Say 1337. Why not? So now, as I mentioned, that when we send a request, effectively we make a transaction. We create a message call. This message call will be sent to that pool of messages or queue of the messages, and then a miner will pick that message and will process it for us and gives us the result. Now, all these things happen instantly in this case because everything runs locally. The miner is locally. So we immediately got our transaction processed, and this is a result that we got back. It's effectively saying to me that, yeah, your transaction got mined, and these are some of the values. Again, I'm not going through all the details at the moment. So the thing is that transaction was successfully performed. Now, for me to verify, I can head and try to retrieve the value by invoking the retrieve function. And this hopefully, well, again, this is another request that I'm sending, and it shows me that the value 1337 was received. Okay, so let's do now something else. Maybe let's try to give it rather than a small number, it's such a huge number, and see what will happen. What if I give it quite a big number? something in this case bigger than int32 range. Why int32? Because if you have paid attention here, this retrieve function, it seems like it will returning a int32 out of a value that is stored int 256. All right. So this value is big enough to be bigger than an int32 range, successfully stored. Now if I go and retrieve this, well, it doesn't really give me the same number back due to the overflow situation that I talked about. Let me store another number, perhaps slightly smaller. See if that's gonna change, perhaps gives us a different idea. So as you can see, the number does not, and the overflow happened and the number does not, well, I'm not retrieving the same number that I have stored there. So the other thing I want to now also try to do here in the lab, we also have, let me go back here. And let's go and open, we also have a number of tests in each lab that will be testing the usability of this contract, like a typical unit test, and the other one is specifically designed to test for that security one. Run them, you can simply run make test. This will run just to make sure that our contract can be successfully deployed and run. So yeah, let's see how this goes. Okay. Now it tries to run the test hello world. And as we expected, we got a pass on that test. Let's have a look at the test itself. Finish. I open the test. So the tests are inside this directory. So test hello world. So this test has been written using Solidity itself. And what it does is a basic test function. First, it deploys, will get an instance of the hello world. Then it will store that number, and it will do this a basic assert equal just to make sure that it's the expected number. All right. Now we have another sets of tests which will test for the security one. But these tests, oops, I just wrong extension at the end, are written in JavaScript because it's a lot easier to test it using JavaScript in this case. And here, as we can see, the first test is we'll check that this contract will throw an exception when the number goes beyond int32 range. To test that, has given this value. And the expectation is that the contract should effectively throw an exception. There are some other tests also here that is incomplete. Let's just run this test. Simply type in make security test. And we expect for these tests to fail. So we got 0 passing and 3 failing case, and one of them is related to that function that that test that I've just went through. The other two, I just left it empty. You can simply just complete them. This is similar. It also needs to throw exception when number is below int32 range. Often they refer to this as underflow, but again, theoretically is overflow. So in this case, you want to test for the minimum range of int32. And we are dealing with JavaScript, right? We have a value called infinity. Why not we test our function against that? And you may come up with something interesting when you complete this test. Okay, so for our case, let's just keep this simple. What I want to do now is I want to now head back to a debugger and debug this bug together to actually really see what happens in EVM when a value goes beyond the range. All right, so to do that, I need to actually head back to my browser and head to Remix. Remix is an online IDE that is quite popular to get started with Solidity programming. And the reason I'm using Remix is when I mentioned debugging, you may have thought about, now I'm going to open up GDB and like tools like that. Unfortunately, at the time of recording this talk, we don't have, GDB does not support EVM. The closest one at the moment does have a support for debugging the EVM is Radar or Radar 2, but I couldn't reliably run it. I got some segmentation fault. So now I'm defaulting back to Remix. Now this IDE does have a good support for low-level debugging, and you can simply also head to this URL, remix.ethereum.org. It will bring that up. But here what I'm going to do is I want to copy over, I want to create a new contract here. So inside here on the left, you hit on this create button, inside the contract, I will create a new file here. Well, let's call this overflow.sol. This is where I'm going to put the sample contract code. And let me just copy over one sample contract here so we can examine this together. Right. Copy it over here. Go. I think I don't need this part for now. Okay, so this contract, pretty simple. Calls overflow. It has a number of variables I have defined here. This is just the helper variables, which we will talk about it a bit later. It has a store function. Again, this is my helper function. I'm not really using it. Effectively, in this contract, I have a function called arithmetic, which effectively adds to a number. Unsigned arithmetic. So I'm just doing an unsigned adding of these two numbers. Left ship and casting from int256 to int30 and exponential. Now, to use this environment, well, after you copy over your contract code, and this you can also copy over the contract code from that hello world example that you got the link to. So you head on the left, you head to this Solidity compiler. We need to select the compiler that I think I haven't copied one line here. I should also do that. That first line on the top, because it will complain the licensing line. You head to Solidity here and select the right version of the compiler. So in this case, I'm gonna start the minimum supported compiler version for this contract, which is 6.10. Right, just wait a couple of seconds, and then you can hit on compile overflow. That now my code is successfully compiled to the bytecode. So the next step is, once we got the bytecode, we need to deploy it to the blockchain. Again, this IDE gives us a browser-based blockchain that we can deploy to. Again, don't worry about a lot of things here. Let me also zoom in perhaps a bit. So yeah, just go ahead and hit on deploy here. Here you see some messages here saying that, hey, our contract was successfully deployed. And the thing right here is an instance of this contract that we can build with. So this is effectively, now I've got that truffle console that previously you saw. I create a instance of a contract and play with it. Now this is example of that, but in my browser. So I will just, as I said, I have this helper function called store. The only thing this helper function does, it just gives me the maximum and minimum range for 256 bit for signed and unsigned. So when I'm testing the arithmetic, I don't need to move around. So you hit on the store, one transaction happen, and now if you hit on these values here, max unsigned, max signed, unsigned, signed, and min unsigned and min unsigned, these are effectively the maximum and a minimum value for a 256 bit that you can use. Let's perhaps go ahead and do a simple arithmetic here. Let's add number 1 to number 2. Type these two in and hit on arithmetic. As we expect, the value 3 was returned, and here we can see the transaction that was used to gives us this value. Now right here, to open the debugger, you hit on debug. This will bring us to the Remix debugger. Quite good in terms of the functionalities that it has for us to do a low-level debugging of this contract. Okay, so the things that I want, so the debugging now effectively happened right on the call where the values 1 and 2 are passed into that arithmetic function. So I'm not debugging the whole main program and setting the breakpoints. So it's nothing like that here. Effectively, we are debugging a transaction or a request that has been already done. Do you remember we talked about that? We have an audit track, we have a persistent storage of all those requests and processes that was done. And that's the beauty of a smart contract, that we can go back and analyze what actually happened. So I'm effectively going back and analyzing or debugging the input to that arithmetic function that I called. So inside my debugger view, so I have a typical debugging function, a step into, a step out, a step back, and things like that. Don't worry about the function stack here. It just tells me I have two local variables called A1 and B2, that is here. Don't worry about the solidity state at this stage. This is effectively the bytecodes that are disassembled to me so I can read it. So these are effectively those code that is being executed by the EVM. And right here, our amazing stack that we're gonna look around, and memory. The other things we don't really need to worry about at this stage. I just close. So there is no register. So if you were expecting to see RAX or RBX, we don't have them here. We just have a stack, and we will see how the stack is used to perform all the operations. The other thing is memory. Memory in a smart contract world is non-transient, meaning at every message call, at every request, this memory is cleared out. So this memory is at the moment contains some value here, but this is specific to this arithmetic function that I call. If I call another function, this memory will be zeroed out. So now let's look at the stack here and see what happens. So these are the instructions. Again, bear with me. After a while, it will make sense to us that what actually they are doing. Since we don't really have registers in EVM, we need to use the stack in a smart way to effectively resemble some of the functionalities that register will give to us. So the instructions, some of the instructions that we will see here are not necessarily related to the actual code that we have written, but mostly related to aligning the stack, freeing up some space on the stack, copying the values to stack for the next operation that's gonna kick in. So, for example, typically at the start of every function, we have these sets of instruction, push 180, and if you remember, push is effectively pushing value to the stack, push 40. I'm not going through all of them at this stage because that will now jump through, but That is effectively the intro to the function that I have just called. So hit on step into. I'm gonna, one thing I forgot to mention, when I call the function, let me go one step back here. So right, go at the beginning. Now, as you can see, the value A is 1, the value B is 2. Now let's examine the stack together. Right at the start of the calling my function, the stack contains two values. Value 2, well, top of the stack, and then value 1. So the arguments that are passed to my stack are from the rightmost argument is on top of the stack, and then following with the argument on the left, which is in this case 1. So the values are already there for my arithmetic function to work. Hit here, and I'm gonna only examine, let's just look at the instructions here and here. Duplicate is, in an x64 world, you most likely have seen a lot of instructions like move, that you move a value from memory to a register, from register to another register. We don't have those instructions here. Instead, we have instructions such as dup, which is similar, which is duplicate, so duplicating a value within the stack, or swapping one value with another value. So duplicate effectively makes another copy of the value that is on the stack. Swapping is just replace two values. So these duplicate and swap effectively helps us to, with perhaps mstore and mload, helps us to implement that move instruction. So duplicate 2 is telling that go and look at the line item, well, the second item on the stack. Here is, let me zoom a little bit more, it is small, and duplicate it to the top of the stack. So let's just hit run. As you can see, number 2, hit on top. And this other one will go and duplicate 4. So like item number 4, 1, 2, 3, 4, which is value 1. And now I expect after execution, this should comes on top of the stack. So I've got value 1 and value 2 now on top of the stack. Effectively, it copied over the arguments to the local environment or the local variable available to that arithmetic function to operate on. And the next instruction is add. Now, x64 word, when an arithmetic such as add perhaps is executed, it will be looking at RAX and RBX to get the operands. But in this case, in EVM word, we are looking at the values on the top of the stack. So in this case, add is an instruction, will receive two values. So the first value is the first item on the stack, and the second value is the second value on the stack. You may be asking where the result goes. Well, we don't even have things like RCX. The result should also goes back to the stack. So behind the scene, once this is done, let me hit that, the result of the arithmetic was also passed back on the stack. And that's pretty much all done. Now we already got the arithmetic. There are a few other codes that are being executed here, some pops and swaps, and eventually a jump which will return that value back to me. Quickly also about the jump. Jump function in the Solidity world, in the EVM, we have a jump and jump destination. It's like go to this location type thing. So for example, now when I hit jump, it will find the instruction that is relevant to that jump as a jump destination, and I land it here. And a few other calls. Eventually there is a return line 608 will be called, and we got the value back. Perfect. Okay, so now let's do something else. Let's go back to our deployed contract here. And this time, what I want to do is, I want to perform an unsigned arithmetic on maximum unsigned value for 256. But I will gonna add 1 to it. So that massive number plus 1. Let's hit it. the value wrapped around. So suddenly we got 0. This is unsigned, so we don't have negatives here. But yeah, so the value wrapped around, we got 0. And let's debug this together. Again, similar to before, we have two values, this int 256 max value and b is 1. If I look at the stack, top of the stack I got 1, then is b, the rightmost value b first, and then a, which is this FFFFF value, 156 bit or 32 bytes. And then a few instructions to get my function running. So let's just step into this, see what's happening. Nothing special. Again, it duplicates 2. So 1 goes on the top of the stack, duplicate 4. This value gonna go on top of the stack, then will kick in. You can see I don't have any other thing on my stack. So once 1 is added to this maximum, the modulus arithmetic kicks in, I get 0. Other instructions, same as before, and all the way back to our return. Yeah. All right. So now we saw behind the scene what actually happens for this, for this arithmetic to operate and this overflow. Now I want to move back and talk a little bit about how we can, effectively prevent this attack. What are the patterns we can follow? Now, since this is a historic bug, there has been a lot of talks around how you can remediate this issue. And 3 common techniques that is used to eliminate integer overflow or any type of numeric overflow is these 3 we can see. One of them is known as precondition check. So before we do the arithmetic, we need to check if that value will go beyond the range of the type that we are dealing with. The other technique is known as upcasting. So we are using a bigger type to perform arithmetic on a smaller type. So say if I'm dealing with int32 type, I will use int64 to perform the arithmetic. So if the overflow happens, I can still catch it. Then downcast to int32. So effectively my bigger type is like a bigger container that I can check if the result of this arithmetic could result into an overflow. And finally, dynamically allocated data types, things like big integer, big int. Now we don't have a simple implementation of big integer, big int within Solidity. So I took that away from our list of recommendations here. So we are limited effectively with number 1 and number 2. One very good news that we have now is that from Solidity version 0.8.0, by default, all the arithmetics, again, all the arithmetic operations are precondition checked. So I will show you an example of that a bit later, that how that is being done. So anytime you use pluses, multiplies, and divisions, by default, when Solidity compiler compiles that function, it will also inject in some additional instructions to perform that range check for us. So that kind of saves us from the majority, not all, the majority of the arithmetic operations, but all the operations that may result into overflow. But prior to Solidity version 0.8.0, we had a library called SafeMath that was widely recommended by the community to use. And this library effectively have the implementation of the precondition check, which I will go through one example right now. So, for example, if we want to implement an add function, that adding 2 numbers, effectively we will simply add those 2 numbers together. but then we'll check that if the result of that arithmetic, or in this case plus, is, well, if it is less than 1, when we add two numbers, definitely the result should be bigger than either of these two numbers. So we will return false, kind of an overflow flag. We say false with the result 0, just to indicate that, hey, there's some exception happen here, or we can even revert the transaction here. Otherwise, we will return true, that, hey, happy days, overflow hasn't occurred, and here is the result back to you. So this is one example of precondition check when it comes to adding two numbers. In terms of casting, well, we are limited to making sure that the value is within that range before we perform our explicit casting here. So in this case, I'm getting a 256 value, and I want to return int32 value back. I've included two checks here. The first one will check that if this number is less than int32 max, less or equal than less int32 max. If not so, it will revert or throw an exception, revert the transaction, and with this error message. And similarly, this other check is checking that if this number is bigger or equal than int32 min. If not so, it will return, well, it will throw an exception with this error message. If all good, I will do a casting back. Now, I want us to learn this because there are cases that the Solidity compiler by default may not help us to protect ourselves against int overflow. So that's why it's important for us to know how we can do a safe precondition check if we are dealing with a specific operation that may overflow. So that's why I have some examples here that we can go through. Let me head back to our IDE again, and I will keep stop the debugger. I will keep the contract as it is, but right in the Solidity compiler on the left, I will change the compiler version to the version that already contains our security checks for overflow. So version 0.8.0. From this version upward, we have the integer overflow checks. Now I will compile this contract again, head back to deploy. I will minimize this instance of contract. I will keep it right on the top, hit on deploy, have another instance of the same contract. Right, open this up. Let me increase this a bit. Right. Hit on the store just for us to get some sample values out. Let's just do something now. Let's just, I didn't change anything in the contract now. Let's just simply go and do a basic arithmetic. Let's just do an unsigned arithmetic of two values. Hit on unsigned arithmetics. As expected, we got 3, and let's head to debug here. Debug this. Okay. Again, on top of the stack, I've got 2, the rightmost value, and then 1 following with 1. Hit on a step into, and this is now a start of my function. Now, you may have already noticed that after the first 2 duplicate, we don't have the add function anymore. Whereas in the Solidity version 6.10, which I compiled before, sorry, 0.6.10, right after this duplicate, there was an add function. It's not the case here anymore. Because as I mentioned now, what's happening here is after these a few duplicates, these 2 values are copied over to this function. So now effectively, we have a local copy of those variables. And now the Solidity is those injected code that will perform the precondition check for us. So again, I'm not going through all of these things at the moment, but effectively this jump will jump to this address that we see here. And I want to take you, after a couple of instructions, there is an interesting arithmetic is done, precondition is done. Now effectively what it's happening here, first of all, it will find out that what is the range of the data type that I have used. So in this case, it will find out that I'm using a 256-bit data type. So then it will find out what is the range for this data type. And once that is happened, here is where the interesting part is done, where the comparison is going to happen. Let's move over. Yeah. So right here, once I reach to this part of the code, I have a duplicate of the second value that I'm adding, the number 2, and with this massive number, which if you remember from the previous deployment, this is the maximum range for 256. So effectively, all those instructions that was done before was to come up with what is this range. It has put it on the stack, and eventually is now going to perform a subtract. So this is another way you can perform a condition that whether this value will end up being an overflow. So far, there is no addition is done. These are all precondition checks. Now, once the subtract happened, so it subtracted that value 2, so the B from that range, and then it will compare that with value 1, the A, and then this greater than, so it will check if this number is greater than this. The result is 0. The is 0 instruction is called. The result is 1 because the result was 0. This is like jump 0. And then it will push the address that the jump will go into, and this jump will happen because we have 1 here as a condition of jump is successful. And we will move here, and now our code is just right here. So the duplicates will happen. I got 1 and 2 on top of the stack, and then eventually the add. So we got 3 back. So all the things that was just done, all those instructions cut a lot more than, as you can see, my actual code, just to effectively check for this precondition. All right, so let me now finish this debugging. And let's do one more example here. We take one massive value, the maximum unsigned, and we add 1 to it. As we know, this must not go through. Yeah. And right here, you can see an error. Revert, the transaction has been reverted. So this is to do with an overflow condition happen, and Solidity stopped it. So those instructions stopped this arithmetic to even take place. So an exception was thrown out that the transaction was reverted. Let's debug this together and see what will happen to that final greater than check. In this case, again, on top of this stack, I got value 1, following my value B and value 1. And let's step into this. Duplicating, copying, making a copy of these 2 values locally, and then this is where now the precondition checks is going to happen. Let's just step into the part that is more interesting for us to analyze. And it's checking what is the maximum size of that data type. There we go. So now, after this duplicate 3, and this maximum range that was pushed, that was identified by instructions for my data type, this subtract will happen, and this will result into this number here. And then this number will be compared with the maximum range of, well, this is the second of this this number is now compared with the second number that I'm going to add. My first number, this is A. So the result of the subtract is compared with A, and then this greater than is checked. Well, the result is 1 because that number was bigger than, A was bigger than result of the subtract. Is the result 0? No, so we got 0 here. The address will be pushed but jump will not take place. And since the jump is not taking place, I'm going now toward a different branch of the code, and this branch eventually will head me into the revert. Okay, sorry, you can't do this because you haven't passed the precondition check. Perfect. All right, so that is pretty much what I wanted to cover. I want to just finish with a few things. One is, I mentioned that Solidity version 0.8.0 by default will protect us against these arithmetic operation, but not so with shift or bitwise operations such as left shift or casting. Let's just run this again together. See what is the result of, for example, left shift. All right, so let's go back to the contract. I'll copy this max unsigned value, and perhaps let's just do the casting of this value and see what we're gonna get back. Not this one, this other one. Sorry, the left shift. So left shift effectively is, if I left shift 2 for 2 times, this is effectively equivalent of 2 multiply 2 power 2. So 2 multiply 4. Or for example, 3 left shift twice, it should give me 12, which is 3 multiply 2 power 3. Sorry, 2 power 2 is 3 multiplies 4 is 12. But if you can shift this with the amount of bits that is available to you. So let's say 254 times. If I shift this, I'm gonna get this big number. But from here on, if you shift it for 256 times, which is effectively the end of the stack, an overflow will happen. The other thing that perhaps is interesting for us to know is, so yeah, this is an example that unsigned left shift is not being checked for overflow condition. The other thing that I want to check here is the cost, the additional cost of operation that is happening due to those precondition checks. Now, one of the things I didn't cover at the beginning, every operation that we do in the Ethereum network is contain a cost, because effectively one of those nodes need to go and process that. And this is known as a gas cost for the operation that we are doing. And the cost happens when the operation that we are performing changes that state machine. So, but all those instructions that you have seen, they all have a cost attached to it. And within our remix, we can see, for example, what is the execution cost of performing, let's go back to this arithmetic, unsigned arithmetic, hit that, and this is the function that was revert. And let's look at the cost of this. So the execution cost of this is 22,487. Now, let me go and open up my previous deployed contract. This is deployed using an older version of Solidity, 0.6.10. I will perform the same arithmetic here. And let's look at the cost of this. 2,200,051. So it's around 3 to 4% less than the cost of the more recent version of Solidity, just due to the fact that the number of instructions, we don't have a precondition checks here. Now, one interesting part here is that if you go ahead and implement your own, so say, let's perhaps move back to Solidity version 6.10, and which does not have those precondition checks by default. And if we go ahead and implement our own precondition check, let's see what's the cost of that. So something like will help out. A plus B, and then we go ahead and do the one bar here. So checking if this value will end up being an overflow. So I need the result to be has to be always bigger than or smaller than 1. So my listing copy. If this is effectively, if this requirement doesn't kick in, the thing will revert and result. So this effectively gonna give me my maybe it's better if I copy this over to my other function here, the unsigned arithmetic. Sorry, what to do. All right, get rid of this. Fix this up, otherwise it's gonna complain. Right. Save. Compile. Yeah, perfect. Now my unsigned arithmetic this time has a precondition check. Right, let's go and deploy this function. So this contract is the third instance of this contract, and I'll get my max unsigned value out. Okay. Let's just try to add a overflow. As we expect, the revert kicked in, so I wasn't able to make this transaction. Now, if I look at the cost, this cost again is still smaller than the cost that we see by default, the Solidity version. This one, other one. The Solidity 0.8.0 will put in. All right, perfect. So I think we have covered quite a lot. One of the things that most likely gonna make sense for us to do is if you head back to the original lab that we have, you can go ahead and start completing. The first thing is you can go ahead and fix it using one of the techniques that we talked about, precondition, or otherwise you can check out the patch branch. This patch branch does contain one example of a sample patch. Apart from that, I'd like to conclude it with this, that we are dealing with, well, a different type of a machine here when it comes to EVM. And integer overflow was the most basic vulnerability that it has quite similarity with this vulnerability in a non-smart contract world that I could explain here. A lot of other type of vulns that we see in EVM are related to business logic, and that needs us to have a good understanding of the whole network, the whole ecosystem of this network, where the way that the messages are passed around, the way that the transactions are processed, the delay that is there between when the request comes in and the response is sent back. And that will end up having a situation where a new type of ones are appearing, and some of the previous ones have a different consequences or different result. That's what I wanted to talk about for today. I hope you guys enjoyed. You can continue still asking us questions by heading to our Discuss platform. Otherwise, feel free to reach out, and I'm looking forward to see you guys at our next workshop. Thank you.